When you tell a drive to decelerate a spindle over a specific amount of time, the drive automatically figures out how much reverse force to apply to get the spindle to slow down within the deceleration time you specify. But did you notice in the previous videos that even though we told the drive to decelerate in 1 second, it actually took a lot longer than 1 second? Why? Well, to understand that, you need to understand how a drive works. In the simplest terms, the drive takes a sinusoidal input, single or three-phase, rectifies it, and sends it to some large electrolytic capacitors to create a DC voltage. In the drive I'm using, the DC voltage runs in the mid 300 volt range. The drive then uses some large transistors called IGBTs to turn the DC voltage on and off in a pattern whose average magnitude emulates a sinusoidal waveform. Because the power to the spindle is controlled by digital on-off pulses, the drive can very accurately control the motor's speed by adjusting the frequency of the pulse waveform. For our spindle, a frequency of 400 Hz gets us 24,000 RPM. We'll use the terms frequency and speed interchangeably in this video since they both tell us how fast the spindle's rotating. Here's the problem. When the drive applies pulses to force the spindle motor to slow down, all the inertial energy built up in the spindle has to go someplace, so it gets pushed back into the drive. If you're familiar with Regen on an electric car, yeah, that's the same thing. That Regen pushes energy back into the large capacitors, which raises the DC bus. The faster you try and decelerate the spindle, the higher the DC bus goes. If that DC bus goes higher than the components in the drive can handle, well, they start to fail and your drive dies. Now, most drives will sense this, throw an overvoltage fault, and turn off the IGBTs. The spindle is then left to spin down on its own. The solution is simple. You just add a high wattage braking resistor. When the DC bus gets too high, the CFW320 drive will automatically reroute any excess energy to that resistor, where the excess energy gets released as heat, instead of raising the DC bus. On the CFW320 series of drives, you just add the braking resistor to these terminals. I also added a switch so we could quickly switch the resistor in and out for our testing. How do you know what size resistor to add? For the CFW320 drive, it's easy. There's a chart in the user manual that says for our drive, the minimum size resistor is 39 ohms at 10 amps, or around 400 watts. It also tells you what size wire to use. Given that, you can go to Amazon and find a resistor that'll work, or I like AutomationDirect.com. They have free 2-day shipping, but you also get their US-based free tech support. Now keep in mind, this is the minimum size resistor, which gives us the maximum power dissipation, which are for the heaviest loads that are being spun up and down a lot in a short amount of time. Is the CNC spindle a heavy load that's rapidly spinning down over and over? Well, no. It's actually a pretty light load that spins down infrequently, so we can get away with pretty much anything here as long as it's the same or larger resistance. Don't drop below the 39 ohms specified. That will let too much current into the drive. I'm using the 40 ohm 400 watt resistor from Automation Direct, so we're good to go. There's links to all the parts I'm using in the description below the video. Well, that's all there is to it. No parameters or configuration required. You just hook up a resistor and everything else is done for you. Let's do some examples. I put a large surfacing bit in the chuck just to add a little more inertia to the spindle. Now before doing any braking, let's see what happens if we let the motor coast to a stop on its own without any deceleration applied. Parameter 229 is the stop method. Set it to a 1 to coast to a stop. And let's go to parameter 4, which shows us the DC bus voltage. Ramp up to 24,000 RPM and hit stop. We see no change in the DC bus because by coasting to a stop, there's no energy being forced back into the drive to raise the DC bus. And it took around 20 seconds for the motor to come to a stop. I'm assuming you're watching this video because you don't want to wait 20 seconds each time you stop the spindle, so I'll go back to parameter 229 and set it to a 0 to enable the deceleration ramp. Now we have not added the braking resistor yet, and remember, in the basic configuration video, we set the deceleration time to 1 second in parameter 101. Ramp up to 24,000 RPM and hit stop. Well, it stopped a lot quicker, but nowhere near the 1 second we specified in parameter 101. And did you hear the pulsing as the motor spun down? Let's do that again, but this time listen to the motor after I hit stop. Ramp up, hit stop. Did you hear it? What was that? Well, that's a cool feature of the CFW320 Series Drive. WEG calls it DC link regulation. WEG's DC link terminology is what most folks refer to as the DC bus. I'll use both, just know it's the same thing. Normally, in any drive, when aggressive deceleration starts, the DC bus rises. In inexpensive hobbyist drives, if the DC bus rises past the overvoltage threshold, the drive shuts down the drive's output, issues a fault, and lets the spindle spin freely to a stop so the DC bus can return to normal. You then have to clear the fault and restart the drive. WEG's DC link regulation adds a second threshold in parameter 151. So now, when there's rapid deceleration and a DC bus hits this threshold, the drive lets the motor coast until the DC bus comes back down. It then restarts ramping until the threshold's hit, where it lets the motor coast again. It does this over and over until the motor comes to a stop. The pulsing you hear is the motor ramping, coasting, over and over. It's kind of like when you pump the brakes on your car when driving on slippery pavement. I'll do it again so you can listen. Ramp up and hit stop. Did you hear it? Before moving on, let's see what happens if we turn off that DC bus regulation. To do that, just push the DC regulation threshold up to the fault level, which in this drive is 410 volts. The DC bus hangs around 340 volts. So as the DC bus rises, it'll hit the fault threshold before the DC regulation has time to affect anything. Let's see. I'll ramp up and hit stop. Yep, the drive faulted out with the F22 overvoltage fault. Exactly what we expected. Okay, let's go back to parameter 151 and get the DC regulation threshold back to its default level. This DC regulation is a really nice safety net for when the DC bus starts to get out of control. And while that's great, we still aren't getting the 1 second deceleration ramp we asked for, are we? Time to employ dynamic braking, where we add a braking resistor to handle the regen energy so we don't get that fault. I'll flip the switch we added earlier to connect the braking resistor. Now you don't have to do anything to enable or configure dynamic braking. It's all automatic and ready to go in the WEG CFW320 drives. Ramp up the spindle and hit stop. Holy cow. It stopped in exactly the 1 second we specified in parameter 101 in that basics video. No errors, no pumping the brakes, nothing. It just works. Let's do that again. Ramp up, stop. Yep, rock solid. I wonder how strong this really is. Let's do something silly and go to parameter 101, the deceleration time, and ask the drive to ramp down as fast as possible. How about 0.3 seconds? Ramp up to 24,000 RPM. Stop the spindle. Wow, it did it. Well, almost. The 0.3 of a second was so short that the motor was still spinning a little after the drive thought it was done. That's still pretty impressive because it did it with no overvoltage faults. Is there anything we could do about that? Yep, it's called DCBraking. You can tell the drive to inject a DC current into the motor, which holds the motor still because the current isn't changing. You can hold the motor before ramping up and after ramping down. On the deceleration ramp, you can specify at what frequency to start holding the rotor, and you can specify the amount of holding current. This is normally used for things like holding big industrial fans still prior to ramping that might otherwise be rotating backwards due to a draft in the room. Holding the fan still before ramping makes it easier for the drive to get the fan spinning and reduces stress on the motor. Let's try that. I'll add 4 seconds of DC braking before the ramp just to show you what happens, and 4 seconds after to stop that excess spindle rotation we saw a minute ago. We'll leave the frequency and the current level at their defaults. Hit start. We see the DC braking in the display telling us it's active, and then the ramp starts. And hit stop. The motor ramps down, and the DC braking stops that excess spinning we had a moment ago. Cool. Now I had to set the Decel ramp time to 0.3 seconds to get this to work. For some reason, on this drive, if I use anything less than 0.3 seconds, DC braking doesn't work. For example, I'll set the Decel ramp to 0.2 seconds. We see the 4 seconds of DC braking before ramping up, but when we hit stop, there's no DC braking at all. Go back to the 0.3 second Decel ramp and hit run. We see the 4 seconds of front end braking. Hit stop, and yep, DC braking works here too. So why doesn't DC braking work for Decel ramps less than 0.3 seconds? Is that some kind of protective feature, or is it a bug? I don't know. Leave a comment below if you know why this is happening. The drive's firmware version is in parameter 23 in case you need to compare. If I figure it out, I'll add a note in the description below the video. What would happen if we remove the braking resistor while trying to decelerate that fast? The DC regulation is still there as a backup. Will it kick in? I switch the braking resistor out. Ramp up. Stop. The drive faulted out. Why? Because the requested deceleration was so aggressive, the DC bus rose too fast and hit the overvoltage fault before the DC regulation could affect the drive's speed. To summarize, the CFW320 braking options are: you can always coast to a stop. You'll never get an overvoltage fault doing that because you're not trying to force the spindle to slow down, so there's no regen energy coming back into the drive, raising the DC bus. The bad news is, it takes a long time for the spindle to come to a complete stop. Ours took around 20 seconds. And of course, it costs nothing. You can have the drive automatically extend the ramp time to protect the drive by pumping the brakes. This gets you the fastest possible deceleration without getting an overvoltage fault or damaging the drive, and without spending additional money on a braking resistor. It's a pretty good compromise, and you won't find that kind of feature in your typical hobbyist drive. You can add DC braking to hold the motor still both before and after ramping. Now be careful not to extend the hold time too long or set the DC current too high. Spindle motors are not designed to run at 0 speed, and they'll heat up quickly, which can reduce the life of the spindle. And finally, you can use dynamic braking, where you add a large wattage resistor to handle the regen energy. This gives you the absolute fastest deceleration with no faults because it can dispose of large quantities of regen energy. But it adds hardware to your system that you have to wire and mount someplace. But you just can't beat it for performance. Here are all the parameters we used in this video. One side note, dynamic braking has its own threshold in parameter 153. It's even more aggressive than the DC bus regulation threshold, ensuring it'll always kick in first if you have a resistor connected. Let's add that to our parameter list. Now remember, other than deceleration time, you really don't need to mess with any of these. I'm just showing them in case you want to tweak them. You won't hurt anything by playing with them because the WEG drives are really good at protecting themselves. Check out these videos to learn how to use the CFW320 drive's digital outputs to automatically control your dust collection system and/or create a drive-ready indicator. If you want to learn more about the WEG drives in general, Automation Direct has tons of tutorial videos showing you everything from quick start to PID to using the built-in PLC. I put links to all these resources in the description below the video.